In this video, we're going to do a little more practice with vectors, and more specifically, some practice with vectors and these different operations on a graph. So first, let's just draw a couple of the vectors here below. We've got vector A here and vector B. And let's first look at A plus B. So we're going to take vector A here. And if, let's say, we're starting right here, we don't really have a position, so it doesn't matter where we put this. But we've got the tail of vector A here, the head here, and if we're adding vector B to that, then the tail has to go there at the head of vector A. So here's vector A, and then we're adding on vector B to the end of that. And so the resultant vector of A plus B is going to be this vector right there. Now if we look at this next one, vector negative B, so I'm just going to copy vector B here. Oops, I don't need to do that. Okay, so I got vector B here, but this needs to be flipped and go in the opposite direction. I need to flip it both ways. We've got the same magnitude here, but now we see it's going the opposite direction. Now vector 2a, well, we're going to take vector A here, and we're going to take a second one. Okay, so we're going to take vector A in this direction. Again, position doesn't matter. We're going to add a second one to it. So vector 2a is actually just one vector, twice the length of vector A in the same direction. Our last one here is vector A minus B, which is the same as vector A plus negative B. That's going to be a little easier for us to look at how our resultant vector is going to be positioned here. So bring a copy of vector A and B down here. Okay, so we've got vector A here. And now this first example, we added vector B to the end of it. So our resultant vector was down here. But we're adding a negative B, which means, like we showed up here, we're flipping it and going opposite direction. So I'm going to flip. So we're going the opposite direction. And now I got to put the tail of vector B at the head of vector A. And so now if we compare to this one here, vector A still looks the same, but now instead of going down and to the right with B, this negative B is going the opposite direction. So now we're going up and to the left, and that resultant vector is going to be right here. Okay. All right, so now looking at a graph, quick review. If we've got a position vector where the tail, the initial point of our vector, matters where it is, unlike the examples we just looked at, we've got the head of our vector, or the terminal point, is going to be some point x comma y. So let's say it's somewhere out here in quadrant 2. So this vector, it's going to start here at the origin. It's a position vector here, just standard position. Starting at 0, 0, it's going to come out to whatever this value is. So we've got this position vector is going to have these two components, where the vector I represents the horizontal change or distance, and the j vector is going to represent the vertical one, and x and y are just it's like the coefficients for I and j for whatever values are in the ordered pair. So this would be some distance x, which is a negative direction, so x would be negative, and then some distance y right here. So we'll look at some examples of what that means. So here we've got three vectors, a, b, and c. So we want to look at what's the relationship between those three, and then which one is a position vector. So it looks like a, b, and c are all the same magnitude, the same length. And since we've got a grid here, we can just kind of count our slope rise over run. So I see I'm going up 2 and over 1, 2, 3, 4, 5 for vector A. So we don't actually have to calculate what this length is. B also goes up 2 and over 1, 2, 3, 4, 5. And C up 2 over 1, 2, 3, 4, 5. So they all have the same magnitude. But you see, based on the arrows, A and B are going in the same direction, and angle C is going, or excuse me, vector C is going in the opposite direction. So relationship here, vector A is equal to vector B, and vector A is equal to negative vector C. So same with B. B is equal to negative C. So if we just flip C around, or if we flip A and B around, those would be equal to vector C. And the only one that is a position vector is vector A, because its terminal point, the tail, or excuse me, the initial point, where the tail of the vector starts at the origin 0, 0. Okay, so now we're going to write vector A as a sum of its components, then as a magnitude and an angle. So it's the same vector that we just looked at. And so we've got, right here, we've got our, the base of our triangle here is, since it's a distance of 5, that's going to be represented by the component 5i, and it goes up 2, so that component is going to be 2j. So vector A as a sum of its components is 5i plus 2j. Remember, in math, we always want to write our variables in alphabetical order, so that's why we always write the I term first and then j. Same as like an ordered pair. We put the x value or horizontal value first and then the y value second. The magnitude, remember, that's this distance here. So if we got a right triangle here with legs of 5 and 2, then we just do Pythagorean theorem. 5 squared plus 2 squared equals this length c squared, and then take square root of 5 squared plus 2 squared. So we get root 29 if we weren't to simplify that to a decimal, if we just leave it in radical form. And then the angle here, well, we can just use tangent, and we're going to do tangent of theta is equal to the opposite 2 over the adjacent side 5. So we do inverse tangent of the ratio 2 over 5, and we get 21.8 degrees, and that would be north of east. So if we're starting east and then we go north direction, that's 21.8 degrees. Or if we want to go from north, from our bearing here, this angle right here would be 68.2 degrees, and we would say 68.2 degrees east of north. Okay, draw vector 2a, then write as a sum of its components. So we're not worried right now about the position. We took vector A here, we added a second one here, so it's got twice the distance, and you see it goes up 2 over 5, up 2 over 5 again, so this is going up 4 and over 10. So we're going to have 10i and 4j right there. So if vector A is 5i plus 2j, we're doubling that, so now it becomes 10i plus 4j. Okay. Okay, so now we want to draw vector A plus vector B. So we still have the same vector A, but now we've got a different vector B here. So we've got 5i plus 2j here. And now for vector B here, if we're thinking about our terminal point here, we're going left 3 and up 4. So if we're going left 3, that would be negative 3i. Up 4 would be plus 4j. So if we were to draw it, we're going to start at the tail of A and go to the head of B. So this right here is going to be the vector, the resultant vector of A plus B. Now, if we were just to look at the components here, the same way we did A and B, we see we go to the right 2 and up 6. So looking at that, that would be 2i plus 6j. Well, let's take a look at if we were to just add these two vector components together. So we can just add these like terms. Right? If we don't have this graph where we can just visualize and count out what our components are, if we were to add 5i plus negative 3i, we get 2i, and that matches what we counted here. And then if we take 2j plus 4j, that gives 6j, and that also matches what we counted here. Okay, so two ways to look at that. We can draw out the resultant vector and then just count those components. Or if we have the components for the vectors we're adding, we can just add the I terms and the j terms together. Okay, I believe we got one more here. So let's find the resultant vector of A minus B and its magnitude. So the last one we just found the sum of the components here, but we're going to find the magnitude of this one as well. We still have 5i plus 2j for vector A, but now vector B, well, we're adding a negative B, right? We don't really want to write or think of this in terms of subtracting. We want to add a negative because now instead of going up and to the left, we're going to flip and go down and to the right. Okay, so now our components change a little bit. Now we're going to the let's see. So these are the components for vector B, but now for negative B, we're going to the right 3 and down 4. So if we were to subtract B, we would take 5i minus negative 3i, and let's just draw this out. This is our resultant vector. So 5i minus a negative 3i would be an 8i, and we can count out 1, 2, 3, 4, 5, 6, 7, 8. That matches. And then 2j minus 4j would give us a negative 2j, and we do go down 2. So that would match there, 8i minus 2j. And then to get that, the magnitude there, we've got 8 and negative 2 as our components, but as a triangle, we would just use 2 and 8. So the square root of 8 squared plus 2 squared would give us root 68, and if we keep that in radical form, that reduces to 2 root 17.